Hi everyone, I am Nidhal Mdini, student from the University of Tunis El Manar. I will present in this video the control with grid forming of a PV-based system for a 4-wire residential microgrid. The study has been performed with our research team KEHNA from Laboratory of Electrical System of INIT. The outline of the presentation is as follows. We start by defining the background and motivation of this work. The system and its model are then presented. The following parts will be dedicated to the theoretical control development, the simulation results, and the experimental microgrid setup, and finally, the conclusion. PV and battery energy storage system are one of the most trending distributed energy systems for residential applications. Knowing that energy production in traditional grid was ensured by rotating machines which have considerable inertia, but PV and BESS systems are zero inertia systems. So, the increasing penetration of energy storage systems and distributed production leads to a reduction of the total grid inertia. The total grid low inertia results in voltage and frequency stability issues. Many microgrid controls are developed in literature to regulate voltage and frequency, especially for load variation and in grid fault. Residential distribution is generally carried out in single phase. This topology creates an imbalance on the low voltage microgrid, since the power consumption is not equitable over the microgrid three phases. Consequently, a current flows on the neutral wire. This imbalance and the neutral power must be taken into account in the microgrid control. The microgrid under study is composed of a PV and BESS system with a DC-DC converter and inductive input filter, a DC bus with two capacitor filters, a neutral leg and an inductive neutral filter, a DC-AC inverter connected to the point of common coupling (PCC) through an LCL filter, a local load, and a utility grid with a 230 phase to neutral voltage and a 50 Hz frequency. Kirchhoff law applied to the input DC-DC filters give the relationship between the first state's variables, which are the battery and PV currents, and the system parameters illustrated in 1 and 2. The third system state variable is the DC bus voltage defined by 6 and given by the differential equation 3. Finally, the midpoint voltage VO and the neutral currents is described by equation 4 and 5. The three-phase inverter output currents and voltages are given by 7, 8 and 9 in an ABC frame. It's most interested to transform this relation in a stationary DK0 frame. The angular frequency of the output inverter voltage omega is the rotational speed of the DQ referential frame. Inverter output current and voltage at a DQ frame are described in 10 and 11. From equations 1 and 2 presented in the slide 6, the battery and the PV currents are presented in Laplace domain by the two relations in the top, which gives a first-order system with the voltage of the input DC filter as input. The DC voltage control is carried out with a cascade voltage current loop. The outer voltage loop with the PI controller provides the current references, and the inner loop defines the duty cycle. A deviation of the voltage VO at the midpoint O will shorten the life of the DC capacitors filters CN1 and CN2. So, the aim of the neutral leg control is to maintain a 0 volt at this point, even if an unbalanced load is connected. This goal is accomplished by regulating the neutral filter current ELN. A cascade to proportional controller are developed for this control. The inverter grid forming control is based on the droop control given by the two equations shown in the top of this slide. In fact, the active and reactive power deviations define respectively the frequency and the voltage variations through the two power damping factor. Droop control is a non-inertia control, so to imitate the synchronous generator behavior, the virtual terms inertia G and tau are introduced in the control loop. The microgrid control algorithm is then described by this flowchart given in this slide. The inputs of the algorithm are the power and the factor power references, as well as the rated values of the frequency F0 and the voltage V0 of the system. The DC bus voltage and the DC bus voltage balancing are performed at the beginning according to the grid state. A power regulation and a voltage and frequency control are developed. In case of a fault grid with unbalanced load, an inertia term are computing and added to the control. The objective of the control is to ensure predefined active and reactive power, while maintaining power quality in the 4-wire low-voltage distribution microgrid. To overcome stability problems of fault grid, the inertia modeling is introduced. Presented results display the regulation of active and reactive power considering the voltage balance in the DC bus. The simulation was performed with PC. It shows the system response of the active and reactive power and the PCC voltage following a power factor variation scenario. The increase in voltage amplitude shown at the second one in the figure in the bottom is caused by the variation in the reactive power. Experimental microgrid setup was conceived for a 20 kVA power system with the 400 volt battery voltage, 800 volt DC bus voltage, and rated values of currents and AC voltage shown in the table at the bottom. System filter sizing was the subject of a paper published in the Springer Nature Applied Science journal in 2020. Filters parameters are illustrated in the table in the left. The PV and battery are emulated by a DC voltage source. The first experimental result gives the current regulation in the battery DC-DC converter control. It shows the performance of the developed PI control. The power variation is achieved by the regulation of the currents ID and IK in the inner loop of the DC-AC inverter control. The ID current regulation is shown at the figure at the right on the top of this slide. The neutral filter current shows a little ripple current. Finally, the PWM signal is presented, which is sent to the power system. Residential microgrids often include battery energy storage system connected with PV system. This study investigates an enhanced grid forming algorithm taking into account the balance of the DC bus midpoint and inertia modeling. Simulation and experimental results are presented to illustrate the effectiveness of the proposed control. Thanks for your attention.